In Chapter 5, Section 4, we'll look at more work with integrals. Now it says indefinite integrals for the title of the section, but we actually start with a definite integral. When you have numbers in the lower limits, lower and upper limit, you get a definite integral. It is defined by the constants that they use. So let's see how we would do this. We'll see various examples in today's section. So we have the integral from 0 to 1 of x times the quantity 4 times the third root of x plus 5 times the fourth root of x dx. Well, the first thing we're going to do is we're going to realize that x is the same as x to the first power, and x, the cube root of x, is x to the 1/3 power. And the fourth root of x is x to the 1/4 power. And what that's going to allow us to do is more easily distribute this x into these terms. And what we're going to get is when you have the same base raised to different powers and you're multiplying them, you add the power. So this will go 0, 1. This will become 4x to the 1 plus 1/3. 1 is really 3/3, plus 1 would be 4/3. Then we get plus 5, distribute this x to the first into x to the fourth. It would be 1 plus a fourth, which is 5/4. And, oops, I forgot the x. This is x to the 5/4. Okay, dx. And now we will use our power rule for integrals, which says add 1 to the power and divide by the same number. So adding 1 to 4/3 would be like adding 3/3 to 4/3, which gives us 7/3. And then we divide by that same number, 7/3. Notice the 4 is out front here. Then we get 5x to the 5/4 plus 1 would be the same as 4/4. So it's 5 plus 4, or 9/4, divided by the same number, 9/4. And now I don't need this integral symbol. I don't need dx anymore because we performed the integral. And now we put from 0 to 1 as the lower and upper limit. Now what happens with these fractions in the denominators, they're going to flip. So 3 is on the bottom, it's going to flip to the top, and this is going to become 12/7 x to the 7/3. Same thing here. You're going to get this 4 to flip up into the 5, and it becomes 20/9 x to the 9/4. And that's from 0 to 1. When we plug in 1, we'll get 12/7 1 to the 7/3 plus 20/9 1 to the 9/4. That's the upper limit. Then it's minus the same numbers, but we plug in the lower limit of 0. And that's being subtracted. But 0 to any power is 0, and then 0 times 12/7 is 0. This whole bottom, this whole second term will be 0. So the only thing we need is the top term. And 1 to any power is 1. So this is just going to give us 12/7 plus 20/9. And you're going to get basically a common denominator of 63. So you'll get 12 times 9. Cross multiply basically, plus 7 times 20 over a common 63. And if you multiply those two terms and add them together, you should get 248/63. At least for my numbers, that's what I get. Okay, so only thing we had to review there was doing multiplication of bases to fractional powers and how we add those powers up. And then the antiderivative rule just says add 1 to the power and divide by that same number. Okay, and that'll be it for number 1. Problem 2 is kind of similar. We're going to have the antiderivative of from 0 to 1 over root 3, so it's a definite integral, of 4 times t squared minus 1 over t to the 4th minus 1 with respect to t, so we say dt. We're going to use a property from algebra that says the difference of perfect squares. If you have a squared minus b squared, you can factor that into a plus b, a minus b. So if we have t to the 4th minus 1, that's the same as saying a is t squared, so we get t squared plus 1 and t squared minus 1. So we can rewrite this integral as 0 to 1 over root 3 of t squared minus 1 on top. The bottom can factor into t squared minus 1, t squared plus 1 dt. Now, difference of perfect squares says I could also factor t squared minus 1 into t minus 1, t plus 1, but I don't need to do that because this t squared minus 1 on the top, and I forgot the 4, there's 4 right here, there's 4 right there. Okay, the t squared minus 1 on top, this whole bubble will cancel with this whole bubble down here, and we're going to get, I'm going to pull this 4 out of the antiderivative, and on top you have 1, a placeholder 1, and then on the bottom we have t squared plus 1 dt. Well, it turns out, and I don't know if I've shown this yet, I sometimes confuse which course I've already shown this to, Calc 3 or Calc 1 or Calc 2. I believe in this course I have not shown this. If you have the integral, let's actually write it over here. So this is just one, I mean, integrals sometimes when they start to look funky, you have to look them up in tables. So we would give you this one, or I'm giving it to you now. I would not give it to you like say on a test. You have to refer to your notes. If you have the antiderivative of 1 over x squared plus 1 dx, that is, the answer is the arc tangent of x plus some constant of integration. But we don't have that constant of integration here because this is a definite integral. But this form here, 1 over something squared plus 1 is the antiderivative of that is arc tangent. So this is going to be 4 times the arc tangent of t, because we're using t as our variable now, and it's going to be from 0 to 1 over root 3. So when we plug in our upper and lower limits, we get 4 times the arc tangent of 1 over root 3 minus 4 times the arc tangent of 0. Now the arc tangent of 0 is 0, and the arc tangent of 1 over root 3 is, you can look at unit circle for this or type it in your calculator, pi over 6. And then we had this 4 out front, so this whole thing will become 4 pi over 6 minus 0, but that minus 0 doesn't matter. So we get 4 pi over 6, divide both numbers by 2, 2 pi over 3. And that would be the antiderivative for number 2. So introduce kind of a new idea here. The integral of this particular form is a arc tangent. So we got some trig functions now. And that's a big part of calculus, is kind of seeing things before. So now you've seen that 1 over x squared plus 1 or 1 over t squared plus 1. The hope is that in the future you'll be like, I think I've seen this before, and then you might think trig, and then you try to look up what is the antiderivative, or what's the derivative of arc tangent, something like that. Trigger your mind. Okay, problem 3 is going to be a straight up, and this one is an indefinite integral, so we don't have numbers for the lower and upper limit. So that means we're not going to get a solid answer at the end. We're going to have a constant of integration that shows up. So I have x to the 1.4, so a decimal power, plus 11 times x to the 4.5, and that's with respect to x. Well, there's nothing new here. You're just going to add 1 to both powers. So this is going to be 2.4 when I add 1 to it, and then divide by 2.4. Well, this one's going to be 11's there for the ride, x to the 5.5 over 5.5. Now, again, because there's no number here on the bottom and top, this is an indefinite integral, which means you're going to get some constant of integration, and they remind us to use capital C. And just keep that in mind. The homework is very picky. If you use lowercase c, you'll get it wrong. They want uppercase C for the constant. Okay, now, the first one there's nothing we can do to simplify 2.4 over 2.4. But it turns out that 11 divided by 5.5 is exactly 2. So 11 divided by 2.5 is 2 times x raised to the 5.5 plus some constant of integration. And that's what we have for problem 3. So it's just our standard antiderivative rule for powers. Just add 1 and divide by the same number. Okay, problem 4. 4 is also pretty straightforward, no tricks here. We have the antiderivative integral. It's an indefinite integral, there's no numbers on it. U to the 7th minus 3u to the 6th minus u to the 4th plus 6 over 9, and then the variable to consider is u, so we put du. So this one's just do each term separately. It'll be u to the 8 over 8, just add 1 to the power, divide by that same number, minus 3, so numbers out in front just stay there. U to the 6 would become u to the 7th over 7, minus u to the 4th would become u to the 5 over 5, plus any constant, you just add a variable to it. So if our variable is u, the constant 6 over 9, just a number, when you take the integral of that, you just add the variable to it. So 6 over 9 becomes 6 over 9 times u. And the only thing I think I did here to make it a little easier to see was I wrote these fractions next to the variables. This is really 1/5 u to the 5th. And then 6 over 9 can reduce to 2 over 3 u. Oh, I forgot this constant, plus c. So that should be the antiderivative of that one. Just writing those fractions out there and then simplifying any fractions that we can simplify. Okay, that'd be problem 4. All right, problem 5. Yes. So we've got a mixed bag here. So we've got the indefinite integral of 2x squared plus 3 plus 4 over x squared plus 1 with respect to x. So I don't usually do this, but I am going to show this one the long way. So each of these terms we can split into its own integral. So this is really the integral of 2x squared dx plus the integral of 3 dx plus the integral of 4 over x squared plus 1 dx. So in effect, what I've done is I've distributed this integral symbol to each of the 3 terms along with the dx to each of the 3 terms. Perfectly legal. So I've made 3 terms being added in one integral into 3 terms being added with their own integral. And I'm going to take it a step further. We can also pull out constants. So this is really 2 integral x squared dx. This is really plus 3 integral dx. This is really 4 integral 1 over x squared plus 1 dx. And the whole reason I did that is to get at this one right here, because I wanted us to recognize that we just saw that antiderivative. And I wrote it on the side of the page, and I said, oh, this one is arctangent of x. So we know this one is 4 times, in fact there's a 4 in that one too, arctangent of x. So that one's done. And then this one becomes 2, antiderivative of x squared is x3 over 3. And then the antiderivative of dx is x. So this is 3x, and then it's plus the 4 arctangent. Now technically, when I break it up like this, each one of these gets, and why don't I show it? This one gets a plus c1, this one gets a plus c2, and this one gets a plus c3. They each get their own constant of integration, because there are 3 different integrals now. But what we're going to say is, well, they're all constants. I don't know what they are. So let's call C1 plus C2 plus C3 just 1C. And so I can account for all those with just one capital letter C. So we're going to get, this is 2/3 x to the third plus 3x plus 4 arctangent of x plus 1 capital C. And looks like exactly what I had for the answer. So that is correct. And that would be problem 5. And I've been kind of showing you honestly the shortcut. Technically what we should have been doing the entire time is doing this. Breaking these into their own integrals and then pulling out constants and then using our power rule. I've been kind of going a little fast and loose with that, just doing it as we go, but this is technically step by step how you would break this down. Okay, that's problem 5. Okay, problem 6. Okay, very similar. In fact, I'll probably break it down again just to keep that theme. So we have the integral, the indefinite integral of 9 sine of x plus 2 hyperbolic sine of x dx. Well, this is, we can break this into 2 integrals, 9 sine of x dx plus the integral of 2 hyperbolic sine of x dx. Then we can pull out the constants, 9 integral of sine x dx plus 2 integral hyperbolic sine x dx. Well, the integral of sine is negative cosine. And the dx goes away when I perform the integral. I don't know if I've shown that in this class. The antiderivative of hyperbolic sine is positive hyperbolic cosine. So it's interesting, in hyperbolic sine and cosine you don't pick up this negative like you do with regular sine and cosine. So we just have to distribute this negative. It's minus 9 cosine of x plus 2 hyperbolic cosine of x, and I should have written plus capital C there, and that would be the answer for problem 6. Won't really go into what hyperbolic cosine and sine represent. You really don't see them too often. I think I came across them maybe a few times in orbital mechanics, but even then it's pretty rare to see those particular trig functions. Okay, 6. Okay, problem 6 is also a trig problem. We have the indefinite integral of secant of t times the quantity 7 secant of t plus 6 tangent of t dt. So we're going to split this in. Well, first we're going to distribute this secant. So this secant's going to go into both of these. So we're going to get secant times secant with a 7 in front would be 7 secant squared t plus, let me distribute the integral 2 as well. And then we get plus the integral of 6 secant t times tangent t dt. Then we're going to pull out the constants, 7 secant squared t dt plus 6 antiderivative secant of t times tangent of t. And this is where you just kind of have to know. I mean, I don't have these. I knew what secant squared was, but I couldn't remember this one. I had to look it up. A lot of times in integrals, you're going to have to look them up. So I've seen literally books this thick that are just integral tables that have thousands of integrals in them. And you just look up the form you have, and it shows you what the answer would be. So it turns out that the integral of secant squared t is tangent t. Not arctangent like we saw before. This is regular tangent of t. And it turns out that the antiderivative of secant t times tangent t is, I have to look this one up, it is secant t. So somewhere we would have shown that the derivative with respect to t of tangent t was secant squared t. And we would have shown that the derivative with respect to t of secant t is secant t tangent t. So I think we probably even saw these exact problems when we did derivatives way back in chapter 3. These are derivatives. We're going this way. So the antiderivative of secant squared is tangent. And the antiderivative of secant t tangent t is secant t. So we get, actually I believe that's the answer. The only thing I forgot was the plus c. So we get 7 tangent of t plus 6 secant of t plus c. Make sure I have the same answer. Yes, that's correct. So that's another thing. You don't really have to memorize integrals if you know derivatives. So if you remember, derivative of sine is cosine, derivative of cosine is minus sine, the derivative of tangent is secant squared, the derivative of secant is secant tangent, then you know the antiderivatives because you just go the other way. Okay, that's problem 7. Okay, problem 8 is a definite integral from 0 to 1/2, lower and upper limits, of, I'm going to write this a little different. They have dr, I'm going to write it on the side, 1 over the square root of 1 minus r squared dr. And again, you'd have to look this up, but the indefinite integral of 1 over, usually you'll see it like this, 1 minus x squared dx is equal to, and this is one I don't have memorized either, I had to look it up myself, it's arc sine. So this one is an arc sine of x plus your constant of integration. So this problem is exactly the same form as this, so all this is going to turn out to be is arc sine. This whole thing is just arc sine. The only difference is x is not our variable, it's r, so we're going to use r. I don't need plus c because I have numbers now as the limits, so it's going to be from 0 to 1/2. So we're going to get, this is the arc sine of 1/2 minus the arc sine of 0, and the triangle ratio of 1/2 gives you the angle for sine of pi over 6. So again, if you've got a calculator that can do that, you can plug it in or go to unit circle, and you're looking for when the second component of the point is 1/2, and you'll see that that angle is pi over 6. And the angle that gives you a triangle ratio of 0 and the sine is 0. So this whole thing just collapses to pi over 6. But you would not, I mean, you get nowhere without this. So you kind of have to know that formula to be able to do this problem. Now in Calculus 2, we'll teach you how to prove that formula, derive that formula. But in Calculus 1, we're not going to ask you to derive that formula. I would just ask you to look it up from your notes. Okay, that's problem 8. Problem 9. Okay, so problem 9 and 10, we're going to have some word problems. Always interesting. So we have water flows from the bottom of a storage tank at a rate, r of t. So this is the rate at which water is flowing out of a container is 200 liters minus 4 liters every, what's the time? Minute. So it starts with 200 liters and it's losing 4 liters every minute. And it says, well, just based on that, it should take at most 50 minutes to drain this tank completely. You can see that if you plug T is 50 into this formula, you'll get the rate is 0 because there's no water left. Okay, and now we want to say what amount of water flows from the tank during the first 30 minutes. Well, it's basically like taking 1 minute, getting a number, then 2 minutes, getting a number, 3 minutes, getting a number, and adding up all these numbers. Well, that is the definition of an integral. So an integral is adding up all these little minutes of loss of water. So we just have to take the integral from 0 minutes to 30 minutes, so they're using 30, of this rate equation. And then our variable is dt. So we're just integrating the rate at which water is flowing out, which will be like a cumulative addition of all of the loss of the water over time. So we get the antiderivative of 200 would be 200t minus 4. This is t to the first. The antiderivative of t to the 1 is t to the second over 2 from 0 to 30. So this is going to be 200 times 30 minutes minus 4 over 2 is really 2. 30 squared minus, plug in 0 now, 200 times 0 minus 2 times 0 squared. And notice this whole thing is just going to be 0. So it's really just plugging in 30. And we're going to get 6,000 minus 2 times 900, which is 1,800. 6,000 minus 1,800, which is equal to 4,200. Units are liters. So in 30 minutes, we've lost a cumulative 4,200 liters of fluid. So that's interesting. So the interpretation above isn't quite correct. So the rate, this rate is in liters per minute. So at time 0, that's when you have the most fluid in the tank and the most pressure. So it's pushing out the fluid at the highest rate of 200 liters per minute. But then it's going to, as the water decreases, there's less pressure pushing the water out at the bottom, so the rate actually slows down. So the rate that the water leaks out of the tank is actually decreasing. This is not quite correct the way I originally interpreted it. This is a liters per minute. So 200 liters per minute to start, and then after 50 minutes it's down to 0 liters per minute because ostensibly the tank should be empty by that point. Okay, so our total cumulative loss after 30 minutes is 4,200 liters. So notice you could, to find out the total amount of water in the tank, integrate this from 0 to 50, and that would tell you how big the tank was to start with. Okay, that's problem 9. Okay, now for problem 10, the last one, it says the marginal cost, which is the cost for producing one additional item. The marginal cost of manufacturing X yards of a certain fabric is C prime is equal to 3 minus 0.01x plus 0.000, there's 5 zeros I believe here, 5 zeros and a 9, x squared. Find the increasing cost if the production level is raised from 2,000 yards to 4,000 yards. So this is going to be our lower limit A, and this is going to be our upper limit B. So we're going to calculate from A to B, which is 2,000 yards to 4,000 yards of this function. So we're taking the integral of this function with respect to yards of material used, 9x squared dx. So we're going to get 3x minus 0.01 x squared over 2 plus 0.12345 9 x to the third over 3 from 2,000 to 4,000. So we're going to get 3 times 4,000 minus, this is really 0.005 when I divide 0.01 by 2, and our x is 4,000 squared now. This one becomes 0.000003. Take 0.00009 divided by 3, you get a 3 here, and then this is 4,000 cubed. Then the lower limit, it's just going to be minus the exact same stuff, but it's 2,000 now. The hardest thing here is just keeping track of these numbers on your calculator. So these bottom 3 numbers, you're going to flip the sign and everything. So it's going to be 6,000 negative. It's going to be positive 2,000 squared times 0.005. It's going to be negative 0.00003, 2,000 cubed. And then the top numbers, take those 3 numbers minus these 3 numbers. And again, if you do this very, very carefully, you should get, at least for my numbers, 114,000. So that's the cost, $114,000 to increase production from 2,000 yards of fabric used in their manufacturing to 4,000 yards of fabric used in their manufacturing. So integrals have a very useful place in business and engineering, construction. If we're looking at water use and things like this, we can calculate these sorts of problems. So that will conclude section 5.4.